In this video, we are going to discuss subtopic 2.2 quantum mechanical model. In this topic, we are describing the orbitals and the four quantum numbers. At the end of these lessons, students should be able to define the term of orbital, explain all four quantum numbers of an electron in an orbital, and sketch the three-dimensional shapes of s, p, and d orbitals. We have understand that electrons are both particles and wave. Now, we are ready to learn about how electrons are arranged in an atom. We know that atom was made up by electron, proton, and neutron. But what exactly are the electrons inside an atom? The position and energy for every electron in an atom is determined by a set of four quantum numbers that describe different atomic orbitals. An orbital is the region in space around the nucleus where there is a high probability of finding an electrons. There are four types of orbitals. There are s, p, d, and f orbitals. The energy of the orbitals are arranged in order of s, p, d, and f. Every orbital has a unique shape, and the shape becomes more complex and difficult to follow as we move toward higher orbitals, and they are look like this. Remember that these shapes are not electrons. It's just a region in space where high probability of finding an electron. Each orbital can hold up to 2 electrons, and the more electrons of an atom has, the more orbital is needed to accommodate the electrons. What is the difference between an orbit and orbital? The orbit is the path of an electron as it travels around the nucleus of an atom. But the orbital is the region in space around the nucleus where there is a high probability of finding an electrons. How to specify the position of an electron in orbital? The position and energy of each electron in an atom is described by the set of numbers called quantum numbers. A set of four quantum numbers are namely as principal quantum number n, angular momentum quantum number L, magnetic quantum number m, and spin quantum number s. Let's have a look for a principal quantum numbers n. Principal quantum number n determines the energy and size of the atomic orbital. They are only represented by a positive integer values, which is 1, 2, 3 to infinity. We saw this when we learned about Bohr model. It represents the energy level of the electrons. Each orbital will have an n value. As the n value increases, the size of orbital becomes larger, and the distance of the electron from the nucleus will be increases. The angular momentum quantum number L is determining the shape of the atomic orbital. The value of L can be 0, 1, 2, until n-1. For example, when n equals to 1, L equal to 0. When n equal to 2, L can be 0 and 1. When n equal to 3, L can be 0, 1, and 2. When L equal to 0, it represents the s orbitals. It has a spherical shape. The s orbital can hold a maximum of 2 electrons. When L equal to 1, it represents the p orbital. It has a dumbbell shape and can hold a maximum of 6 electrons. When L equal to 2, it represents the d orbital. This orbital has a cloverleaf shape, and it can hold a maximum of 10 electrons. When L equal to 3, it represents the f orbitals. This orbitals has a double cloverleaf shape and it can hold a maximum of 14 electrons. But drawing this orbital is not required in our syllabus. So we can summarize that when the value of L equal to 0, it represents the s orbital. Thus, it has a spherical shape. When L equal to 1, it represents the p orbital and it has a dumbbell shape. When L equal to 2, it represents the d orbital with a cloverleaf shape. And when L equal to 3, it represents the f orbital with a double cloverleaf shape. Let's take a look for an example. If the n value is equal to 2, the possible L value can be 0 and 1. When L equal to 0, it is the s orbital. Thus, the orbital is namely as 2s orbital. When L equal to 1, it is the p orbital. Thus, the orbital can name as 2p orbital. When the n value is equal to 3, the possible L value can be 0, 1, and 2. When L equal to 0, it is an s orbital. Thus, the orbital can be named as 3s orbital. When L equal to 1, it is represent the p orbital. Thus, the orbital can be named as 3p orbital. When L equal to 2, it is the d orbital. Thus, the orbital can be named as 3d orbital. Now, let's discuss the magnetic quantum number m. Magnetic quantum number m determines the spatial orientation of orbital along a standard set of coordinate axes. It indicates the maximum number of orbitals per energy level for a particular value of L. The value of m can be from negative L to L. For example, when L equal to 1, the value of m can be negative 1, 0, and 1. This represents 3 orbitals. When the L value is equal to 2, the m value is negative 2, negative 1, 0, 1, and 2. This represents 5 orbitals. When L equal to 0, m must be 0. It shows that it consists only one s orbital with only one orientation. When L equal to 1, m can be negative 1, 0, and 1. This means that this consists of 3 p orbitals, whereas they have a different orientation such as px, py, and pz orbitals. Each orbital have the same size, shape, and energy. When L equal to 2, m represented by negative 2, negative 1, 0, 1, and 2. It consists of 5 d orbitals, but different orientation, which is dxy, dyz, dxz, dx square minus y square, and dz square orbitals. Each orbital have the same size, shape, and energy. When L equal to 3, m can be negative 3, negative 2, negative 1, 0, 1, 2, and 3. It consists of 7 f orbitals with different orientations. But remember that we don't need to draw the f orbital since it is not required in our syllabus. Orbitals split up into degenerate orbitals, which is having the same energy and size. For example, 3s is lower energy compared to 3px, 3py, and 3pz orbitals, which shows that 3px, 3py, and 3pz have the same energy and size. Now, let's discuss about the spin quantum number s. The spin quantum number s determines the direction of spinning motion of an electron in the orbital. The direction can be either clockwise or anti-clockwise. S can be positive half or negative half. Each orbital can hold up to 2 electrons. The maximum number of electrons that can occupy in each orbital are shown below. The s orbital only consists of one orbital. Thus, it can hold up to 2 electrons. For p orbital, it consists of 3 orbitals. Therefore, it can hold up to maximum 6 electrons. The d orbital consists of 5 orbitals. Thus, it can hold up to maximum of 10 electrons. And finally, the f orbitals consist of 7 orbitals. Therefore, it can hold up maximum to 14 electrons. This table shows the possible value of n, l, m, and s with a certain number of the electrons that can occupy in each of the orbitals. Now, let's learn on how to write the sets of quantum numbers. When the value of n equal to 1, the L can be 0. This represents the s orbital. When m equal to 0, this shows that only one s orbital is present. This orbital can accommodate up to 2 electrons. When s equals to positive half or negative half, thus there are 2 possible sets of quantum numbers. When the value of n equal to 2, L can be 0. This represents the s orbital. When m equal to 0, this shows only one of 2 s orbital. This orbital can accommodate up to 2 electrons. But remember, the size of orbital increases with the value of n. The larger the value of n, the larger the size of s orbital. The possible value of s can be positive half or negative half. Therefore, there are 2 possible sets of quantum numbers. When the value of n equal to 2, L can be 1. This represents the p orbital. The possible value of m can be negative 1, 0, and 1. This shows that there are 3 2p orbitals. This orbital can accommodate up to 6 electrons. When s value is possible to be positive half or negative half, therefore, there are 6 possible sets of quantum numbers. When the value of n equal to 3, L can be 0. This represents the s orbital. When m equal to 0, this shows only one 3s orbital. This orbital can accommodate up to 2 electrons. Remember that the size of orbital increases with the value of n. The larger the value of n, the larger the size of s orbital. The possible value of s can be positive half or negative half. Therefore, there are two possible sets of quantum numbers. When the value of n equal to 3, L can be 1. This represents the p orbital. The possible value of m can be -1, 0, and 1. This shows that there are three 3p orbitals. These orbitals can accommodate up to 6 electrons. When the possible value of S can be positive half or negative half, therefore, there are 6 possible sets of quantum numbers. When the value of n equal to 3, L can be 2. This represents the d orbital. The possible value of m can be -2, -1, 0, 1, and 2. This shows there are 5 3d orbitals. These orbitals can accommodate up to 10 electrons. The possible value of S can be positive half or negative half. Thus, there are 10 possible sets of quantum numbers. Let's check a comprehension.